Let's do this guy. Okay. All right, so I suggested redrawing the circuit every time. Well, from here, you can see that these two obviously are in parallel. These are in series. And when I take, yeah, so let's go ahead and add those right now. In series, that's just going to add up to 4. So if I redraw once, ah, I've got this scenario. So that becomes 4, still 2, 2, and this is 2. Now I'm going to add these in parallel. And bring that again. When I add that in parallel, that's 1/2 plus 1/2 is and then the reciprocal of that. Oh, that's right, because this is 4. Sorry. Oh my gosh. I think I put 2. Maybe I didn't. I don't know. Uh, I hope I didn't put 2 there yesterday because in my notes it's 4. Otherwise, it would just be 1, the answer, and that's not what I have. So that's 4. I guess we could do both, but if this actually is 4, then it's going to be 1/2 plus 1/4, which is 3/4, and the inverse of that. But anyway, let's just do it again. Yeah, so I get this. If that's actually 4, then this would be 1.33 repeating ohms. If it's 2, then this guy's just 1, right? Because it would be 1/2 plus 1/2, which is 1, and then the reciprocal of that, which is 1. As it stands, it's 1/2 plus 1/4, which is 1 is 3/4, and then the reciprocal of that is 1.33. Now all these are in series, so they just add up. So that's going to be 4, 2, yeah, 7.33 for the total equivalent resistance. So if I redraw it again, this is a circuit that I have. Final time is 8 volts, and this is 7.33 repeating ohms. So R and Q is equal to 7.33. Yeah. So that's what I have. So in the notes I should have, and if it weren't, it would be 4 plus 1 plus 2, which is 7 ohms. If this guy were actually 2, so you can go from there. But I'm gonna just stick with this. Now, to get the full current coming out, it's just Ohm's law. So I would do, that's I'll call it I1. So if that's I1 coming out, then one, two, then I1 is going to be equal to, so it's delta V over R, but in this case, it's going to be the voltage of the battery, 8 volts, divided by the total resistance, 7.33 would be. So I1 I1 is equal to 1.09 repeated. And I guess that's going to be amps, is it? Everything else is ohms, yeah, so amps. Yeah. And now that current goes and it splits, so it goes through both of these, gets here, and at here it splits. So here we're going to have, let's say, I2 and I3. Now, it doesn't split. I guess, yeah, I'm just going to do the ohms law method. So you first get the total resistance over this, total voltage over that thing, which that voltage would be this current times that resistance. So that voltage is going to be, so I'll call it delta V 1.33. And that's going to be equal to I1 times basically 1.33 ohms. And so delta V 1.33 is equal to, now by the way, I'm not truncating anything here, although I need to go back and save that. So I'm going to store this one. Go back and calculate. Yes. Okay. That voltage is 1.45. volts. Now, if that's the voltage on this guy, and that's the reciprocal resistance of these two in parallel, and the voltage on resistors in parallel is the same, and is the same as the equivalent voltage. So it's the same voltage on each leg. So to get I2 is going to be equal to this voltage, 1.45 repeating, divided by 2 ohms. I2 is equal to, still coming to 0.7 Q amps. Three is going to be 1.45 volts divided by the other resistance 4. So this ought to be half of that. 31.5. 36. So 0.36. And that seems to be consistent with what I have in my notes. So yeah. So it's kind of a piecemeal process you have to go through and do it like that. Yeah. Yeah. Yeah, that's it. um, we can do the other one. Let's do that. I think I give them number 4 here. I don't really have much space over there. Maybe I can draw it. Or something like this, 8 volts. Okay. Well, this whole thing here, this thing here is this resistor is in parallel with that whole thing. Obviously, these two in parallel, and all of this is in series with that guy. Okay. So, yeah, usually I'll start as far away, maybe from the battery. I guess what I'll do is put these together, and then put that and this together, and then that's the final thing. So, redrawing it a couple times. On the first one, we'll get so here I have the 5 ohm. And that's going to be 5 ohms. When I put these together, that's 1/3 plus 1/3, and the reciprocal of that. So 2/3, I guess it's 3/2 then. So is that 1.5? I think it is. 1/3, 1/3 plus reciprocal. Yeah, 1.5. So this is going to be 1.5 ohms. And then I do that with the reciprocal thing with those guys, and then redraw again. So 1/5 plus 1 over 1.5. So reciprocal again, like 1.15 something or 0. And some other stuff. Again, keeping it in the register. Now these just add, and I've got the final. That's going to be like 6.153. This is 8.0 volts. And if we get the I going around, okay. So I'm saying the equivalent resistance down is the whole thing. REQ is equal to, yeah. So that's going to round to 6.2. Oh, 5. This is because I'm doing 2 significant digits. That's the thing in each. When I first started, I only have 2 significant digits. So this goes to 6.2 ohms. Now the current here, I'll call it I1. I1 is going to be equal to the voltage 8.0 volts divided by 6.2. Now that's, I'm keeping the whole value here. So keep that in mind. I1, 1.3 amps. Now you just got to backtrack. So at this point, so I'm going to have like 5 currents here because current splits once here. And I get, this is I1 coming out. And here I'm going to call that I2. This is I3. But then I2 is going to split again. Actually, we can do that in our head because whatever that is, since these resistances are the same, it splits equally. So we just call that the fourth current. But I have to figure out basically these two currents. And again, what I can do is figure out the voltage across the equivalent resistance, and that's going to be the voltage across each one of those four legs. So, and I can also then go one step further and say that that's also the voltage across each one of those legs, whatever the voltage is from the 1.5. So I just figure out this voltage here. And it's going to be current 1 going through that guy. One step closer to that. So the voltage on this is going to be, I guess I'll call it the voltage on delta V on the 1.15 resistor is equal to I1 times 1.153. And so delta V 1.153 is going to be equal to I1, where did I put it? Oh, it's right here. I didn't put it anywhere. So let me store that in register 2. Store 2. So it's going to be that guy times I1, which I put in register 0. Yeah. Does not feel right. I think I got turned around. So and I need my pointer. Where is it? Turn it. Stimulating the face. Okay. Somewhere here along I got turned around. I have to go back, but that's where the pictures help. So the resistances, I think I'm pretty cool with. But that first current, so the total equivalent resistance, we'll say it's 6.2. Yeah, because it's the 5 times 1.15. Okay, and I put that in register. Put that in register 1. So times 8 So, okay, current 1 is 1.3 amps. And that 1.3 amp goes through that thing, so the total voltage across that should be this times the 1.153, which I placed in register 0, what we call in times. Is that coincidental? Because I'm getting 1.5 volts, but it's also 1.5 ohms. That's what's throwing me off. I didn't write all these little details. I just put the answers. So it also has 1.5 volts across it, even though it's 1.5 ohms. That's just very coincidental. But I get it could. That just piqued my interest. So it coincidentally. Oh, but that's this whole thing. That's yeah. So yeah, okay. So this thing right here has 1.5 volts across it. But that means that has 1.5 volts, which is 1.5 ohms, and that has 1.5 volts. Okay. Which means that if that's the case, then the current that's drawn down there is just 1 amp, because that's going to be the current on this is going to be voltage divided by resistance, right? I2 is equal to delta V over the 1.5, this thing, which is 1.5, divided by its resistance, which is 1.5 ohms. It end up being 1.0 amps. But I don't think that's what I have. I have 0.5 amps. I have half of that. So something's. Well, what I know is that the voltage across this and the voltage across that has got to add up to be 8 volts. So let's take a look. Do some checking here. So that current, which I'm saying is 1.3, if I multiply by 5, I put that in register 2, so we call 2, and 5. 6.5 and 1. Yeah. I guess I could have gotten it wrong unless I had another different value of resistances or something like that. I definitely have 1.3 amps coming out. Well, what about that voltage? Saying this voltage here, or this current I3, would be the 1.5 volts divided by 5 amps, or 5 ohms, which is 0.3. That's also what I have. So I have that being right. And so the currents then must add up. Oh yeah, I guess so. That adds up. It would be if 1.3 amps goes in, then 0.3 amps goes across here and 1 amp goes through there. So I don't know what I have in my notes there. It looks like maybe I can't read it very well, but it looks like it's 0.5. Oh, because that's through each one. My bad. Yeah, duh. It's got to split again. Okay. Yeah, duh. So, yes. So there's 1 amp that goes through that guy, but that guy has to split again into basically 2 more currents, I4 and I5. So I guess I just put the final answer there. And I can do the Ohm's law method, or I could just use my intuition, because since I have equal resistances, that 1 amp splits equally. So it splits into 0.5 here and 0.5 there. All right, so that's it. Yeah. So I2, I'm just going to name them the way I did. So I2 does end up being 1.0 amp. Okay. And I3 I3 is going to be its voltage divided by resistance. So the voltage across that guy, which again is 1.5 volts here, here, and here. So 1.5 volts divided by 5 ohms, which is 0.3 amps. And then that makes sense because at this node, we know that I1 that goes in is got to equal to I3 and I2 coming out. I1 is 1.3 amps. So then 1 amp plus 0.3 amps is 1.3. So that checks. And so then through the 5 ohm resistor, we have 0.3 amps. And so the last thing is we go back to the last picture. So 5, 1.3 goes to that. And here, you can call that I4 and I5. They just split. I4, I5. What we can say is that I4 equals I5 equals 0.5 amps. So I think that's everything. We don't really need this because it's not actually through a resistor. It's just on this picture, I2 would be here in this leg. So there's nothing there, no resistor there. And technically I asked for the current through each resistor, not through each leg, but whatever. Yeah. And then I3 comes across here. And I1 is here. So I1 is 1.3, I2 is 1, I3 is 0.3, I4 and 5 are 0.5 amps. So that's the kind of thing you do. I think I gave you one more. I'm just going to write the answers down because that was even easier, I think, than these last two. But for this one, 10. I don't know if I gave that to you. I don't remember giving that to you. I don't think I did. I think I just gave these. So I'll leave it at that. But there's plenty of examples in the book. Remember, you can also do the chapter problems, which is, I would suggest that, and as opposed to the Wiley plus homeworks that are assigned. And cool. But we probably need to go into the Kirchoff method. That's actually the a method that is a bit more powerful and something that I need to spend a little time with that in class. Yeah. Now, basically, the difference is that, or the way that you know you need to use Kirchhoff's rules. If I were to use Kirchhoff's rules for these, it would be overkill. You could do it, but whenever you can tell what direction the current is flowing, then you can do Ohm's method. When you can't technically tell that, then you should do Kirchhoff's. And the way you know that is if I just have one battery in an entire circuit like this, I know how the potential hill looks. But let's say that I put another battery over here, maybe in a different polarity. I might not really know how the voltage is, flowing. And so that becomes kind of an implicit unknown, the direction of flow. Even though current is not a vector, still by knowing the orientation of the flow of current, I basically know the orientation of the voltage in each leg, or what is the direction of the slope of the potential hill, so to speak. And So that allows me to set up these equations implicitly. But that's a problem if I have more than one battery and I don't really know that. So Kirchoff's rules allows you to work out the problem without knowing that information. And again, if you, yeah. And you still have to, it's kind of like Newton's laws. If you still have to choose a direction of flow, but if you're wrong, then Kirchhoff's rules that shows you that in that leg, that current was just in the opposite direction. It was a negative sign, a negative of what you chose. So yeah. And Kirchhoff's rules, there are basically just two rules. And one of them we kind of already know. It's the current rule. I just said it here. What goes in comes out, like at that node. And then there's the voltage rule, which we'll talk about. Let's go ahead and write down the rules for that. And then I will show you some examples. So that's technically this method that we just did. It doesn't have a name, but I call it the Ohm's law, the Ohm's method, just because you're using Ohm's law everywhere. That's the last equation that allows you to be able to solve for unknowns in any particular leg. So that's just my kind of pet name for that method. But Kirchhoff's method is definitely the name of that method. It's what everyone refers to it as. And it was, I don't know the history of the physicist, Mr. Kirchhoff. I think he was German, though. There you go. We found a specific place for this. So I'd like to have a more powerful. So I'll just, Kirchhoff's rules, there are two of them. Kirchhoff method of circuit analysis. The first rule is that it's the current rule or the nodal rule, which is that the sum of all currents entering a junction must equal the sum of all currents leaving the junction. Or otherwise, there's a violation of charge conservation. And remember, that's a violation of energy because charge is energy. We see that from, well, charge is not energy, but charge is energy per unit voltage. Charge has energy to go around. So I guess technically charge is energy per unit voltage. But voltage is energy per unit charge, so whatever. It's the amount of potential energy. It's say that charge is proportional to potential energy. So if somehow the charge dissipated, that means that that energy would just be dissipating or being spontaneously created for no reason. So it would be a violation of ultimate conservation of energy as to why that's true. So what energy goes into a node must come out, and so what current goes in must come out. So the sum of currents into a node equals the sum of currents out of the node. And so I could dramatize that like this. I say that we've done it over here, but just to be specific right here, if I say that I1 goes in, and I2 and I3 must come out. Over here, I2 has to go in, I3 goes in, so I1 must come out. And so mathematically, I could state that as here. Oh, look, I want to do it on this page, so see this better. I'll put it on the inside. I3 and 3. So what we can then say is that I1 equals I2 plus I3. And that becomes a mathematical statement for this particular example of Kirchoff's current rule. And let me write the name. I didn't set it, but I didn't write it. Overall Kirchoff's method. This first guy here is the current or nodal rule. All right. Now we'll do the loop rule. Loop or voltage rule. It states that the sum of all voltages around a closed loop in a circuit must be equal to 0. And again, it's the same reason as the current rule. Voltage is defined as energy per unit charge. So voltage is proportional to energy. I don't think I need to write that. Hopefully it's starting to become part of your short-term memory now. Voltage, potential difference. We define it as change in potential energy of a charge per unit charge. And we've been describing voltage as energy per unit charge all along. So it's proportional to energy. And if you start at one point, it's kind of like saying potential energy, right? If I'm and we did this with in mechanics a while back. If I have this thing on the ground, we know that gravitational potential energy, one form of it, assuming that G is constant close to the surface, is just mgh, right? It's just force times distance. If you pick something up through a distance, the work done on it by gravity is mgh. Mg, the force, gravity. Now I'm forcing on it, but gravity is also forcing on it. So if I move at a constant velocity and assuming no friction in my hand, which there is, but again, the work I do is also mgh. So that becomes a potential energy function. We know that through one round trip for a conservative force, no work is done. It's the same. It's basically that rule is kind of a kind of a statement of the loop rule, actually. So gravity does negative work when I pick it up through h, but then positive work when I let it go down. So minus mgh, work done by gravity, plus mgh, work done by gravity. When I get back here, the total potential energy is 0. So the loop rule is kind of, it's that, right? Because you could think of it, again, you can think of the charge as moving around the circuit. It's like I told you there's an electric field in there. The electric field is a conservative field. So you can think of the thing either falling down a potential hill all the way around, or you can think of it being accelerated by the electric field in the wire as it goes around the loop. So since the force on it is ultimately a conservative force, then if I'm in the same, if I just circumvent the circuit, and by the terminology that I taught you, I think is traverse. Traverse means to scan through a leg of a circuit visually and analyze. So just by doing that around a loop, I'm going to get, the potential energy of the thing is got to be the same in those different positions. So let's work out. So the sum of voltages around a closed loop of a circuit is 0, meaning we have a total energy change of nothing, which should be the case. Otherwise, you're spontaneously creating energy. I guess it would be energy somehow in the system, but the system really is the field. So somehow the field would be fluctuating. And that could be the case, but we're assuming that everything is static here, static field, static constant field, static. So in a static field, which is the assumption, like if I'm varying the voltage, then that would be true. But then by varying the voltage, you're actually taking energy in and out of the area. So anyway, nothing's changing. So externally in the field, and so therefore the charge should see no spontaneous increase or decrease of energy as it moves around the loop. Anyway, but we have to figure out how to count up the voltage. How do you add up the voltage? You have to have specific rules to do so. And it's basically common sense and logic how we set up the rules. So let's say that we have a node A and B. We have a resistor in this thing, and the resistors are, and I would have to know the direction of, so here I'm assuming the direction of current is going to be flowing in this direction. So call that I. So remember that current is just charge per unit time. So essentially, when the current, these actual charges move through that resistor, remember they have to pay toll. And the toll that they give up is a certain amount of energy to get through it. So they're giving up that energy in a minus sign. How much energy do they give up? Well, it's really how much energy per unit charge do they give up, which is voltage. So the change in voltage of a charge going through that, first of all, it's got to be negative, because in the direction of current, I'm going down the potential hill, so I'm giving up some of my voltage. And it's just the amount of voltage is just associated with Ohm's law. It's just going to be that current times that resistance. So the idea, verbally, you would say, whenever you traverse a resistor in the direction of current, you have a loss in voltage equal to that consistent with Ohm's law minus IR. So I guess that delta AB is going to be minus IR. For this same problem, if I were to, and I guess we have to make a standard here. So in this problem, I'm traversing from left. We have to, because I'm establishing the definition. So this is traversing from left to right. In fact, in all of these examples I'm going to give, let's make a caveat to say that we're traversing from left to right. I think I have that in my notes. Yeah. So assume circuit element. Because that makes a difference. um, in these examples. Okay. Yeah, so I guess I'm just going to change the example around just to, so I'm traversing the left or right. So if I have another circuit, and I would just call it AB again, where the current is in the opposite direction, um, the current is going in that direction. But now we're going to still traverse from left to right. So now when I scan across, kind of like the, for some reason, I always think about salmon swimming upstream in this case. But I've got a gain potential, right? I'm going up the hill. Got a now the charge um, is not going up the hill. The charge is going to the left, but you're traversing it. So it's like, how does the voltage, as I scan across, what would the voltage be doing? What would the change in voltage of the charge be across that resistance as I scan? Well, it's going downhill. So if you go up, the actual, because you can think of, certainly the charge has voltage, but there are certain points in the voltage that have a potential energy. That's what's kind of different from the analogy that I made here, because, well, I guess it actually is the same. If you specify certain potential energy planes, they decrease, the potential energy planes increase as you go up. So that's kind of what we're looking, even though, the object isn't there. Like if it were there, it would establish certain potential energy planes. So it's kind of, I don't know. It's like that. I can't stop at a loss of words to explain it any better than that, but I think it's obvious, pretty intuitive. Certainly would have to be. And so if we came over here and traversed from right to left, that would be the same thing. We'd have a plus IR. So it's working out in terms of the signs. Um, in this particular example, I'm keeping the the direction of traversing the same and changing the current. And it's either vice versa. But over the years of teaching, for some reason, it seems to me that it's easier for students to grasp if I keep the traversing the same and change the direction of the current. So I hope it's not throwing you off. Uh, and again, traversing, that means scan scan the circuit visually and as you analyze the circuit. So again, traversing from left to right, going to go through the resistance resistor opposite the direction of current. And so the change in voltage for that from A to B, that's direction of traverse, is going to be equal to plus IR, the gain in voltage. Now, I'm not writing that out verbally because I'm assuming that these equations will be enough for you to remember that. Um, but, it said the same thing here. Basically, well, I guess maybe I could write it out. Why not? If you traverse, first of all, let's remind you of that definition. Traverse, visually, visually, scan a circuit in a particular direction or orientation. Direction slash orientation. All right. And so the rule is that traversing a resistor in the direction of current yields a voltage loss. I'll say with current yields a voltage loss. And obviously the opposite is true. Traversing a resistor opposite current gives a voltage gain. So it's kind of counterintuitive, but again, that's why I think of salmon. Salmon going up the hill, they have to gain potential energy. Going down the hill, they lose potential energy. Um, that did I just say salmon? Yeah, I'm from South Carolina. Sorry, my little uh, country dialect came through. Uh, I do know that it's a silent L, so I meant to say salmon. Uh, um, yeah, so traversing tell you a funny story about Southern dialects. Traversing a resistor opposite. So I said with yields. So with current yields a voltage loss. Got so caught up in my thing that I didn't finish the sentence. So with current, abbreviate that voltage loss. Traversing resistor opposite current yields a voltage gain. All right. The only other thing we study right now is a battery. And so we have to put that rule in too. And that's pretty obvious because you just follow the polarity of the poles as you traverse across it. So for a battery, right? If I have a battery in a circuit like this, again, we'll say A and B traverse from left to right, plus minus. Obviously, I'm going down the potential hill as I traverse from left to right, high potential to low potential. So delta VAB here would be equal to a minus delta V of the battery. And for this scenario, where the battery is turned around, again from A to B, traversing from left to right, I'm going up the potential clearly from low potential to high potential. So in this case, I think yeah, delta AB. And remember, delta AB is final minus initial. So even though I'm writing it AB, it's final minus initial. That implies I'm traversing from left to right. So that would be a plus delta V. If assuming, well, actually, let me do this. Let's call the imp here because this is actually, as we said the other day, the imp is actually the true battery. The delta V is if you have the return on resistance in there, it decreases a little bit. So I'll write this. I think that's what I actually have in my notes too. Yeah, it is. So we'll call it just so we can distinguish between the deltas V stuff and it's not confusing. So the imp is actually, I'm going down the hill from left to right. So it's a minus imp. And here I'm going up the hill. So it would be a plus imp. I traverse from left to right. So that's how we add up the voltages in the circuit as we go across. using Kirchoff's rules. All right, so yeah, I got a couple examples here that we can do to illustrate the power of Ohm's law, Kirchhoff's law rules. First, I have a little simple example here. I want to show like the difference in why putting a battery in a circuit. And this one, it's so simple, you probably could tell it. You probably could tell, what the answer is without doing Kirchhoff's rules, but this is what I want to, it still shows a really nice illustration. And then we'll go on to a few more complex problems. We'll do this simple problem 2 different ways, or do it and then tweak it slightly. And we'll go ahead and use Kirchhoff's, even though Ohm's method is probably the easiest way to do it. And certainly in the first example, since I'm only going to put in 1 battery, that's all I really need to do. But it does show you that you can't use Ohm's method for more advanced circuits, because it won't give you the right answer necessarily. And again, you'll be doing it and you won't know that it's nothing in the mathematics that's going to tell you it's the wrong answer if you apply it that way. But Kirchhoff's method is the most powerful, it's more comprehensive. So you can use that for complex circuits, or you could use it for easy circuits. It would just be probably more work than is necessary if it is possible to use Ohm's method. Anyway, examples. So let's start off with this simple example where I have basically just 1 battery, and I could use Ohm's law, Ohm's method. So we're going to make this 5 amps, 5 ohms, 5 ohms, 2 ohms, and 5.0 ohms, 2.0 ohms, and 10.0 volts. Now here, I can definitely. Why is that thing just switch spontaneously like? Oh, there we go. How are you?
I'm good. How are you?
Good. I didn't know anyone was in class.
No, I just came in.
Oh, that's what it is. Okay.
Yeah,
All
every
right.
time I get a chance, I'm like, let me go to the class.
Let me do an example here, and then I'm gonna do a couple, and then I'm gonna set you up to do some class examples, class problems. So what I wanted to show you here is the necessity for and why it's crucial to be able to use Kirchhoff's laws. So if we basically we need to figure out the currents. I mean, we could, you could do equivalent resistance, but that's not necessary for this method. So basically in a circuit, what you want to know is what the currents look like. So here I just make a choice. I pretty much know what direction is going to be here, but if you don't, you just make a choice. So here I will say the current I1 will come here, and then it splits, and I'll take I2 here and I3 here. I3 and then I2. So the first rule, the first equation, so we have 3 equations we need. We have 3 unknowns, I1, I2, and I3, so we definitely need 3 equations. And we can apply either rule to get either of those 2 equations. So I'm going to use, out of this circuit, you're only going to get 1 current rule because you have 2 nodes, so it's just going to be 1 current rule. And that is that I1 equals I2 plus I3. So that's my first equation. Now I'm going to use Kirchoff's loop rule to get the other two equations. And I've got three possibilities. I've got the inside loop here that I can do. I've got the inside loop here, and then I've got the overall loop for the whole thing. So I only need two, so I'm going to do the inside loops. And that'll be my other two equations. So you start anywhere in the loop. So I'm going to start here. I'm going to go around the clockwise direction, this loop, and add up all the voltages specific to the rules that I laid out for you. So here I go, if I'm going in the clockwise direction, I'm going through this battery from right to left. So that's from the minus to the plus lead. So I'm going to get, that's going to be plus, and it's 10 volts. So that's plus 10 volts. And then go around, nothing there, nothing there. Now here I've decided that current is going from left to right. So I'm traversing from left to right as well if I'm going around in the clockwise direction. So as I go through that resistor, that's going to be a voltage drop. So minus I2, whatever that is, times that resistance, which is 2 ohms. And that's going to, and then when I get back to my initial position, I've got to equal 0. And that's the loop rule. That gives me my second equation with the current in it. And then I do the same thing here, starting anywhere I want here, go clockwise. And it doesn't matter if you go counterclockwise, it still should work out, but I just usually do the same orientation for each loop. So through this guy, in the traversing in the direction of current, I'm going to have a minus I3 times that resistance, which is 5, and then nothing, nothing, nothing. Now I'm going through this second resistor opposite the direction of the current I chose. So that's plus I2 times 2.0, and then back to my original position equals 0. All right, so it's just a matter of solving those equations simultaneously. And here, probably what I'm going to do, I can see it here. And again, we didn't really need this kind of overkill to do Kirchhoff's rules, but this is one equation I want to know, so I can get I2 here, I can plug I2 into this equation, get I3, and then I2 plus I3 equals I1. So I2 is clearly going to be 5, right? Because solving this guy, I'm going to have I2, basically take it over, I have a minus 10, and then divide it by a minus 2.0. So I2 is going to be equal to 5.0 amps. And it's positive, which means that I chose the correct direction for that current. If it were negative, that would have meant that it was going opposite the direction that I chose within that leg. So now I can solve equation 3 for I3 and plug this in. So if I do that, I3 is going to be equal to a minus I2 times 2 divided by a actually plus, no, minus, sorry, minus 5.0 ohms. And so that's gonna, yeah. So you can go ahead and finish that, and I'll go ahead and finish, and then I'm gonna tweak it, and we're gonna do it again. Right back. All right. Yeah. So yeah, sorry. So what is that's going to be? Yeah, so we do I'm doing here. Sorry, I lost my train of thought. Oh, sorry. I am multitasking. Not the best at that. So if I take 2 ohms and plug it in here, that's going to give me that I3 is equal to, so it's going to be positive. So that's 5 times 2, 5 amps times 2, yes, ohms, divided by 5 ohms. So that's going to be 2 amps. Yeah. So I3 is equal to 2.0 amps. And since it turned out to be positive, that's also in the direction that I chose, which sense. And so then I add them up. I just take equation 5 and 8 and plug them in here. 2 plus 5 is 7 amps. So that would give me I1 is equal to 7.0 amps. A lot, but is that right? Actually, that's not right. What's going on? That's not what I have here. 14 nines, 10 nines, and 4 nines. Why? Oh my gosh. Why do I always do that? This is right. I left off a resistor here and from what I have in my notes. So this is right for that. You know what? Why don't we do this? Yeah, so that is correct. So I'm going to tweak it. I was going to just tweak it once, but I'm going to go ahead and put that back in because I think that makes a difference with the tweak that I really want to make. Anyway, it just gives you practice. So you see how how I did that. So why don't you try it again? And I'm going to put another resistor in. And again, with just tweaking it here, we still could do Ohm's law with this first tweak, but because this is the original problem that I really wanted to do. But still, it just gives you an opportunity to practice and see if you get the answer I get. So let's do a different circuit where I'm just going to put a resistor on this leg, on that corner. So so what is it? 5 ohms. So that's 5 ohms. This is 2 ohms. And this is 5 ohms. Right? Yeah. And then this is still 10 volts. So go ahead and do Kirchoff's rules again. Basically, it's very similar. The current rule is going to be the same, right? Call that I1, I2, and I3. So I1 is equal to I2 plus I3. Why don't we take these same loops here again, these inside loops? That guy, that guy. And yeah. So here, starting here, going through, I'm going to have a minus I2 times 2. And then now here, well, obviously I1 would be coming out. So we have to kind of think about that a little bit. I1 would actually be coming out here. So if I'm going to traverse in the clockwise direction, then I go through the 5 ohm, this 5 ohm resistor in the direction of current. So that's also a minus I1 times 5.0. Then back to the battery and I'm up, so plus 10, and then back to my original equals 0. That's a little bit more complex. And over here, then, this is going to be the same. That's going to be going in that orientation. I have minus I3 times 5.0, right? And then now plus I2, and then 2.0. And back to my original position equals 0. So a little bit more complex. I have to now kind of do some magic. I have to solve. It gives a little bit more, shows how these. Here, I could just solve for I2 directly, but here I've got two unknowns. So I've got to do some manipulation. So what I would do is add the two equations. I've got minus I2 2.0 here, plus I2 2.0 here. When I add them, I eliminate in favor of, well, that would just make I1. Yeah, so that really won't help. I guess probably what I would do is I would substitute equation 1 into, I mean, honestly, you could probably do the Ohm's law method for this, but just to give you, yeah, let's just go ahead and do that. What you could do is plug I1 into, actually, I probably would do that. I probably would add the two equations. So then I would have I1, well, it doesn't matter, yeah. Because if I plug I1 into this, then that's going to give me an equation that just has I2 and I3 in it. And then I can solve those two equations simultaneously. That's probably what I would do. I mean, I don't know. Another thing I could do is I could add these two equations, and then I would have the I2s cancel out. Then I would have something that has I1 and I3 in it. But that would, yeah, then I would have to make, I think the way to go is to just take I1, put I1 into this equation, and that's going to do the algebra, and then that gives me two equations with two unknowns, I2 and I3, that I can solve simultaneously. That's the route that I'm going to go. That is the route that I'm going to go. But So let's do that. Yeah. So sometimes I put little notes to let me know, how I'm flowing. So I'm going to put 1 into 2. So that's going to give me, so the minus I2 2.0, and then minus quantity I2. I'm just going to do it in my, steps as I go out. So I would have I2 plus I3 in here, so times minus 5. So that would be um, a minus I2 times 5, and then a minus I3 times 5, and then a plus 10 equals 0 with I2. Yeah, so now these two combine, and I have minus I7, or minus I2 times 7, and then minus I3 times 5, and then plus 10 equals 0. So now what I can do is, I haven't used this one yet, so I can solve that simultaneously with that, because I have I3, I2, I3, I2. And maybe the route to go would be to, yeah, you have to play these little tricks. I have a minus I3 times 5 here and a minus I3 times 5 here. So what I could do is multiply the basic, subtract the equations, or same thing as multiplying this by -1 and adding it to this equation. And then the I5 would go out, and I could just solve for I2. So yeah, so I could say something like equation 3 times minus, yeah, I don't know, I'm gonna look at the computer. Well, minus equation 3, sure. So if that's the case, I'm gonna make that equation 6. So that's gonna be I3 times 5 minus I2 times 2.0 0. Now if I add that 6 to 5, the I3 goes out, and so I'm gonna have a minus I2 times 7. And then this is going to come down minus I2 times 2. And then I still have the 10 over there, which is plus 10 equals 0. And so I think this is going to be consistent with my notes, so we're on the right track. So that's 9. So that's a minus I2 times 9.0 equals, if I take the 10 over, that's minus 10. And the minus signs cancel, and I have that I2 is equal to 10 ninths. Yeah. So what I would suggest, you don't have, just keep it as a fraction, because all the information is there. If you truncate it by trying to round and, you're just going to lose information. There's no reason to do that. So generally speaking, you do end up dealing with fractions in these. I do anyway, because I keep it like that. And so, yeah, irrational numbers. So I2 now, I'm going to plug it back into either one of these equations. I could put it back into this guy, and that's going to give me what I3 is. Actually, I'll put it back into here. So putting 9 into 6, I'm going to have, so it's 10. I'm going to have I3 times 5 equals, when I take that over, that's plus, and then I2 is 10 ninths, so I'd have 10 ninths times 2, and then divided by 5. So I'll do that over, I don't think we need that anymore because I want to compare it to this. Yeah, so the next one I do, I'm going to compare it to this one. 11. So then that's going to be I3 equals 10 ninths times 2, but then dividing by the 5 here, 5. So yeah, that's going to end up being 4 ninths. 5 goes in 5 once, 5 goes in twice, so 4 ninths equals I3. And so I1 then, well, I1 is going to be equal to I2 plus I3, which is 10 ninths amps Venus in the plus 4 ninths amps. So I1 is equal to 14 ninths amps. So that's how to do Kirchhoff's rule, Kirchhoff's method in its kind of full-blown glory. It's a simple problem, so I really could have done Ohm's law, but maybe it's easier. It's nicer to show you with a simple problem. The kinds of it's linear algebra. Basically, this is what you do, and these problems are very. You do a lot of. You have these in linear algebra, and you can actually use more advanced mathematical methods to solve this. You could set up a matrix with these equations, these 3 equations. This guy, and this guy, and do matrix methods to solve it. Again, overkill for simple problems like this. I don't usually teach that because we don't usually do problems that complex, but you know, in an advanced electrical engineering class, like a junior level physics class, or electrical engineering, or E&M, you might probably would propose that method to do, because you can get pretty crazy circles, right? And algebra, like this method is too cumbersome for me anyway to do something like that. Oh, okay. Now, I'm going to tweak this by putting a battery in here, in the opposite polarity. So yeah. And then with Ohm's law, it would be a little bit difficult. I don't even know. I've never even tried it, but if there's 2 batteries in different legs, then I just do Kirchhoff's rule. And so we can see how it's going to tweak based on flipping it around. So right now we have I1 is 14. I2 is 10 ninths. Let's remember that. In fact, I'm going to erase the work and put the results by this diagram. And in the new diagram, I'm going to have to work it out, and then we're going to compare the answers because there's going to be some shifting around. And this is really what I want to show why, just like I teach last semester with conservative and non-conservative forces. I have 2 methods of applying the problems. And from the beginning, if you have conservative and non-conservative forces doing work on the system, you know which one you can use, either conservation of energy or the modified work energy theorem. Here, if you have more than one battery in various legs, just use Kirchhoff's rules. Don't even try the Ohm's law. So yeah, so this new circuit is going to look like this. It's going to be the same thing, but with a battery also in in this second leg here. I'm making that 10.0 volts. I'm making, what is this? I mean, 10.0 volts as well. And all the resistances stay the same. 2 ohms here. Here, this is 5.0 ohms. And up here, this is 5.0 ohms. Okay. And we can use the same method that we did before in terms of analyzing the circuit. So why don't you work on that? Why don't you try to make some headway with that for a few minutes? And that's just, what I'm gonna do is the same circuit to loops. So I'm gonna do the current rule, which is gonna be the same, and then the loops rule, which will change slightly because of that guy. So I'm going to also erase all of the work and just keep the results here because I want to be able to compare the different currents in each leg just by adding that tweak to the resulting circuit that we have over here. And so for this guy, we'll say that I1 is equal to 14 9 amps. I2 is equal to 10 9 amps. And I3 is equal to 4 9 amps. And also keep in mind that because the signs all came out positive, it means that the orientation of the circuit, of the current in this circuit, is the actual orientation that I chose. Let me make this red so it pops out more. We can see it a little bit better, or purple or some different color. So I1, I3, 3, and I2. Oh man, why do I keep doing that? I2. All right. All right, so give that a shot. I can erase all the rest of this stuff too. What did I say we were going to do? Yeah, so again, 1 into 2. That's going to give the 10. The minus I2, 6. And then minus 7 times I2. And minus 3. Or minus I3 times 7. And then equals 0. So minus I2, 7, minus I2, 6 is 13. So 10 minus I2, 13. And minus I3, 7 equals 0. Now look at this. I'm going to set this up like this. I'm going to take the 10 over on the other side. So in fact, that's interesting. Yeah, I don't have a. Oh. Yeah, you'll see something like take the 10 over, be minus 10. So this equation will become numbering again over here. So 6. It's going to be, if I take the 10 over, it's minus, and I subtract through, multiply through by minus sign. I have I2, 13, plus I3, 7 equals 10. And if I take this 2 volts on the other side for this equation, then I have a minus, or I have a I2 times 6. or minus I3 times 5 equals 2.0. And that's how you, that's what it would look like to begin to set it up like a matrix. You have three columns, the I2 column, the I3 column, and then you have the voltage on the other side. So, yeah. As I said, I'm not doing that method, but just to show you how, the possibility of what that would begin to look like if you wanted to go that route. Here, we're going to continue with the linear algebraic manipulation. Let me get rid of this. And we'll keep that result. Oh, this is a different problem, so we don't even need that anymore. Okay. So you got to find a common denominator. I'm thinking 35 because here I can multiply this equation by 5 and this equation by 7 and then add those two results, and that would take out the I3. So yeah, you just have to look at it like that's the linear algebra type stuff. So multiplying this guy by 5 and this by 7, that will yield, so I2, 5 times 13 is, was that 65? Yeah, 65. And then 35. So I3, 35 equals 10. And then 9, we've got 42. And then minus the I3, 35 equal, oh, sorry, it's not 10, it's 50. Whatever. And then 7 times 2 is 14, right? 14. And now you just add the two equations, and I get I2 times 107, 107, and then that's 0, and then this is equals 64. So I2 then is equal to 64 over 107. Hmm. Problem. Something's wrong. I don't think that's what I have in my notes. That doesn't simplify to. Oh man. My notes, I have that to be. Oh, is there a minus sign? So that would have been 42 minus. I missed a minus sign here. So this equation came from here. I just rewrote it. No, what? You know what? I just messed up. I just got screwed up. I don't know what happened. I copied something down erroneously. When we got here, I did have a 0 over there too, didn't I? So oh no, it's this. Oh yeah, so I took the minus sign over and both things became plus. So that was this. And then this came from the equation that I hadn't used yet. Yeah, that should have been plus, right? Because I was going. Don't know why it's not. Yeah, write down some different numbers. 2 volts, polarity, 10, 5, 6, and 7. I guess I chose the current in a different direction. Maybe that's why it should still work out. That's wrong. 5 times this guy is 50 plus 15 is 65, and then 35 and 50. 7 times 6 is 42, right? Yeah. Now I'm adding the two equations because I don't need to subtract because that's still negative. I get the 64. Maybe I had it wrong in my notes. I don't see a mistake here. And I don't have all the details in my notes. Yeah, so I'm gonna keep rolling with that. Third time's a charm. Let's just check back through. Plus 10, minus, minus, and minus, minus. All right. Yeah, okay. I did make a mistake in my notes. I definitely don't see one here. Make sure the algebra was right there. So when I came here, I took this guy, substituted into here, and that was 2 minus signs. So where is it? Oh, here. 1 into 2. So 10, that's minus. And all those are minus because that was minus. And then 7i2, 7i3, combining minus 7 and minus 6 is minus 13. The 10 is plus, because it was plus from here, taking it over on the other side. That'd be to be also minus. So you have a minus 13, a minus 7 equals a minus 10. So all the minus signs would cancel, and I've got this. And this one, I'm just writing that down again. Plus 6 volts, and this again, it was plus because of, oh, wait a minute. That came from, oh, that came from this equation. Yeah, so I'm going here, minus 5, minus 2, and then plus. I've chosen that direction, right? So when I get over here, it's plus, minus, and then when I take the 2 over the side, it's plus. Yeah. So common denominator, I can get it here if I multiply. 5 here, 5, 35, 7 here, minus 35. Add equations, that's 0. 50 plus 14 is 64. 60 plus 65 plus 42 is 107. Yeah, I think I got it wrong in my notes. I think we're gonna go with that right now. Um, so, yeah, we then go for, you just take that I2 and plug it back like into here. So from 8, I3 should be equal to 50. Take this guy over here. Well, I'm gonna have 50 and then minus I2 times 65, and all of that divided by 35. So that's going to be 50 minus I2, which is 64 107ths times 65 divided by 35. So you're going to have to do a bunch of stuff with common denominators and stuff. So or 160 107. So you'll have 50 minus 4160 over 107 divided by 35. I get the common denominator here, which is just multiplying by 107. So 50 times 107 5, 5, 350. So 5, 350 minus 4160 over 35. Sorry. Over 107 over 35 is going to be equal to 1190 over 107 over 35. which is the same as I3 divided by something is the same thing as multiplying by the reciprocal. So I3 will be equal to 1190 over 107 times 1 over 35. 35 goes into 1110 evenly, I believe. 35. Yep, 35. So you end up with I3 equals 34 107s. So, and again, I really want to show you this trend because even though you have to work with fractions, some people don't like that. You just brush up on it. Just brush up by doing it. It ends up working out like that. You start getting these irrational numbers that have common denominators like that. It might take a little work to get to it, but it just works out that way always. That's why I like to keep it as a fraction. And so now when I add them, I've got I1. I1 is just going to be, what is that, 98? 98 107s, just by applying this formula here. So I1 is equal to 98, right? 60, yeah, 98 107s amps. So unless I made a mistake, that's what I'm getting right now. I don't know. I don't have that in my notes. I think I might have made a mistake in my notes, but whatever. All right. So that's Kirchhoff's rules. Kirchhoff's rules method of circuit analysis. I guess that brings us to, I think I started about a few minutes late with the lecture, so that makes up that time. I think this is a useful class. I'll do something new. Okay, well, that's that. Have a great weekend, and I will see you next week.